to the video on Introduction to ARM processors. In this video, we will be studying about history of ARM processor and the features of ARM processor and versions of ARM. Into history of ARM processors. The first ARM processor was developed at ARM Computer Systems. Called as ARM Computers Limited of Cambridge between October 1983 and April 1985. ARM then stood for Acorn Risk Machine. It was called as RISC because the architecture was basically reduced instruction set computer. So it was called as Acorn Risk Machine. Later, the acronym expansion was changed to Advanced Risk Machine. In 1990. The name was changed because it was taken over by Advanced Risk Machine Limited, and this Advanced Risk Machine Limited was a joint venture of Apple Computers, Acorn Computer Groups, and VLSI Technology. Later, around 1991, the ARM introduced ARM6 processor, and it was basically used in Apple Newton. So it was in 1991 that ARM6 was introduced. Subsequently, additional companies like Texas, ST Microelectronics, and others used ARM processors into their mobile phones, into the computer hard disk, personal digital assistants, and many other consumer products. And we must note that the ARM does not manufacture the processor or sell the chips directly. Instead, what ARM does it will give the processor designs to its partners based on the ARM low cost and power efficient processor designs. The partners can create their own processors or microcontrollers and system on chip solutions. And this business model of ARM is called as intellectual property licensing, abbreviated as IP licensing. So in addition to the processor designs, ARM also licenses systems level IP such as peripherals, memory controllers. To support the customers who use ARM products, ARM has developed a strong base of development tools, software and hardware products in order to enable the partners to develop their own products and to enable software developers to develop software for ARM platforms. Going to features of ARM. ARM supports 32-bit instruction set, and it also supports 16-bit compact code called as thumb instruction set code. So processors can function as both 32-bit processor and as a 16-bit processor. As the name itself suggests, the ARM processors are RISC-based architectures. Although ARM is RISC-based architecture, it also has CISC features. So, since it is RISC-based architecture, I can say that it is following load store architecture. Now, going into load store architecture, if there is an instruction in memory, ARM processor will not take the instruction directly from memory, execute it, and it will not store back the result into the memory. Rather, whatever data is available in the memory, that will be brought into one of the registers of the ARM processor, and the required execution will be performed, and the result will be stored back into the register, and later the value in the register will be stored back into the memory. Since the values are loaded from the memory, executed and stored back into the memory, it is called as load store architecture. And since it is RISC-based architecture, we can say that the instructions are fixed length. Since we are using a load store architecture, wherein we require a large number of registers, the ARM processor also supports for large number of registers. There are 16 32-bit registers, and the registers are named as R0, R1, R2, so on up to R15. The next feature of RISC-based architecture is most of the instructions are single cycle instruction. That means to say the instruction takes one cycle for its execution. The next feature is the instructions are implemented in hardwired implementation. We will have to note that most of the operations like addition, subtraction, multiplication with accumulation are all single cycle. Only division operation takes around 2 to 12 cycles, and again it varies. Going to next feature, just like the desktop that uses Pentium, most of the mobiles and pocket PCs uses ARM. ARM processors have high performance. It has around 300 million instruction per second, that is MIPS, for a very small die space of around 0.15 micrometer. And the program counter is mapped to, as I told you, there are 16 registers. All the 16 registers are 32-bit. Starts from R0 to R15. R15 register is meant for program counter. The main purpose of program counter register is to store the address of next instruction that is to be executed. And register R14 has a dedicated function, and it is link register. So the main purpose of link register is the program counter address will be transferred to this link register on any functional calls or on interrupts. Next feature of ARM is with respect to its memory. The ARM processors has both Princeton as well as Harvard architecture. ARM 7 family has got Princeton architecture and ARM 11 family has Harvard architecture. The difference between Princeton and Harvard is if there is a single memory to store both program as well as data, we call it as Princeton. If we have separate memory to store program and data, we call it as Harvard. But remember, although it is Harvard architecture, in ARM processor, there is one big memory of around 4 GB, and in that memory, few locations are allocated for data and few locations are allocated for program. In single memory, we have bifurcation for program and for data, whereas the buses that we use will be different for program memory and data memory. So that is how it is following Harvard architecture. So I can write it like this. ARM follows both Princeton as well as Harvard architecture. Harvard is used in ARM 9 and ARM 11 processors. Princeton is followed in ARM 7 processors. And it can be stored as Word. Let me say Word is 32 bits. In ARM processor, the naming convention is 8 bits are called as byte, 16 bits are called as half word, 32 bits are called as word. So since it is 32 bits, I can write it as B3, B2, B1 and B0, where B3 is 4 bits, B2 is 4 bits, B1 is 4 bits, B0 is 4 bits. ARM can either use little endian format or it can use big endian format. It can be defined at program initialization or it is based on the microcontroller manufacturers. So when I say little endian format and big endian format, it differs in the way the bytes are stored in the memory. So in little endian format, let me say that 0020 is the lowest address, 0021, 0022 and 0023. These are my address of the memory location. If little endian format is followed, the LS byte, least significant byte, which is B0, will be stored in the least address. Then B1, then B2, then B3. The same thing if it is big endian, let me say the memory location is again the same 0020, 0021, 0022 and 0023. In big endian format, the most significant byte that is B3 is stored in the least address. B3, B2, B1 and B0. So little endian format and big endian format will vary in the way the bytes are stored in the memory. So we can say that ARM has got programmable word alignment and it can be programmed as either big endian or as little endian. See, CISC instructions can be supported for programming, but the internal implementation is always on 32-bit RISC code. These are some of the important features of ARM processors. Going on to architectural versions of ARM and families of ARM. ARM has got many versions and it starts with ARM 1, We have ARM2, so we can call it as ARM V1. V stands for version. ARM V1, ARM V2, ARM V3, ARM V4, ARM V5, ARM V6, ARM V6M, ARM 7. We also have ARM V7M. Going on to families, why do we have to have so many versions? ARM has got so many versions of processors, and each versions differ in their architectural features. So going on to families, ARM version 1, the family is one of the example is ARM1 processors. For ARM version 2, the examples are ARM2 processors and ARM3 processors. For ARM version 3, examples are ARM6 and ARM7 processors. For ARM version 4, the examples are ARM7 TDMI, and this is the most popular architecture, ARM7 TDMI and ARM9 TDMI. Going to ARM version 5, examples are R7EJ and R9E, also ARM10XE. Going to ARM version 6, examples are ARM11. Going to version 6M, let's study what are these things again. So 76M, we have Cortex series, Cortex M0, Cortex M0 plus, and Cortex M1. Cortex M1 will give assistance to FPGAs, that is field programmable gate arrays. Cortex V7 examples are Cortex A series, I will call it as Cortex AX, and Cortex RX. Cortex V7M examples are Cortex M3 and Cortex M4 processors. So these are the versions and families of ARM processors. Now let's go on to ARM processor division based on its performance. So ARM processors can be classified as classic ARM processors, as embedded Cortex processors, and as application Cortex processors. Now we will be rating it on the y-axis we have performance, and functionality. On x-axis we have capability. Coming to classical ARM processors, under classic ARM processors we have ARM 7, ARM 9, and ARM 11 processors. Under embedded Cortex processors, we have Cortex M0, Cortex M1, Cortex M3, and Cortex M4 processors. All the four M1, M4, M3, M1, M0 are used for microcontroller applications. So we call it as microcontroller profile. Apart from M0 to M4, we also have Cortex R series. I'll call it as Cortex RX. Again, there are three types under this Cortex R series. One is Cortex R4, Cortex R5, and Cortex R7. Cortex R4, R5, and R7 in general, Cortex R series is used for real-time profile. Under application Cortex processors, we have Cortex A5, Cortex A17, and Cortex A53. Apart from this, we also have Cortex A15, Cortex A57, Cortex A7. Remember, Cortex A5, Cortex A7, and Cortex A53 has got high efficiency, whereas Cortex A15, A17, and A57 has high performance. Moving on to naming conventions, as we told, we have ARM 7 TDMI, ARM 7EJ, ARM 9E, ARM 10XE. Now, let us understand what are these terms meant for. X in general tells the family of ARM. Y tells the memory management. Z tells cache memory. T stands for Thumb 16-bit encoder. D stands for JTAG debug. H stands for um, M stands for fast multiplier. I stands for embedded ICE macro cell in circuit emulator macro cell. E stands for enhanced instructions. When we say enhanced instructions, it provides support for DSP instructions, so it is enhanced DSP instructions. J stands for Jazzle, that is, it provides support for JavaScripts. F stands for floating point unit, and S is for synthesizable version. And in general, V stands for version. Let us now move on to some detailed comparison of V7 to V4 to V7 processors. Let me say V4. After V4, V4 thumb, V4T, then we have V5, then we have V5E. With the V5E stands for V5 with enhanced DSP instructions, then V6 and V7. So ARM processors can execute in two modes. One is called ARM mode and another one is called thumb mode. In ARM mode, it will act as 32-bit instruction. In thumb mode, it will work with 16-bit instructions. So let me call ARM mode. ARM mode will have 32-bit instruction and we have thumb mode. So we have not shown V1 to V3. V1 from V1 it was introduced with version V1. The ARM processors had 32-bit instruction alone. But later, in order to improvise on the code density, they introduced even 16-bit microprocessor. 16-bit, they provided support for 16-bit instructions. Let's see the changes in all these versions. So when ARM processor was introduced, it was with 32-bit instructions. So in 64T also, same instruction set continued. But when it went to version 5, there was slight improvement in the instruction set. In version 5E, they introduced enhanced DSP instructions. That is why it is abbreviated as V5E. Then in version 6, SIMD memory support was added. SIMD stands for single instruction multiple data. Then in version 5 it was enhanced further. So it can be shown like this. Then thumb mode was introduced in 740. T stands for thumb version. So in 740 thumb instructions were introduced. In version 6 it was slightly improvised. And in version 7 thumb 2 was introduced. The difference between thumb and thumb 2 is in case of ARM mode and thumb mode, in all the previous versions, there was a requirement to switch between ARM mode and thumb mode by using branch instructions. Since it was time consuming and so they decided that it has to be improvised automatically, they should be switching from thumb mode to ARM mode. So in thumb 2 instructions, there is automatic switching from 32-bit instructions to 16-bit instruction mode, that is from thumb mode to ARM mode.